Okay, here we are with the second day. You should realize that functions like we've been working with sines, cosines, e's, functions from a list, including our laminated sheet, can involve substituted values. What I mean by that is you can take out sine of x and replace it with sine of 2x or sine of x squared, and the formulas still work. You can also combine series using multiplication and division, which is really cool. And again, I'll show you some examples to make this make sense. Okay, we're going to find a Maclaurin series for f of x. You're basically just using memorized formulas. Hopefully they are memorized formulas. If not, you got to get cracking. All right, so I don't have a formula on that laminated sheet for e to the 4x, but I do happen to have one for e to the x. And you should know what e to the x is. It's 1 plus x squared over 2 factorial, and so forth. With the e to the x's, the signs don't change. The powers keep matching the factorials. The coefficients are always positive 1. And basically that goes all the way up to however far you want to go. I'll just make it generic. It's going to be x to the n over n factorial. Okay, so that's e to the x, which is awesome, except we didn't want e to the x. We wanted e to the 4x. Well, that's easy. All we'll do is we'll just change all the x's to 4x's. There we go. So writing it in sigma notation, we would have e to the 4x equals, and then we have a sum. Again, this is an infinite sum, so we can put an infinity up top. And for the index, we're going to go n equals 0. I always like to try to do the easiest part first. I can see that in the denominators, it's just going to be n factorial, because really there's an invisible 1 factorial. 0 factorial is defined to be 1, so it's going to be n factorial down there. Up top, this is going to be a little trickier. We do not have an alternating component, but it's simply going to be, I guess it's not terribly tricky, 4x, the whole thing, to the n. Because again, this right here is 4x to the first. 1 is 4x to the 0. Anything to the 0 is 1. So that is our sigma notation right there. Now, of course, the book can be a little tricky, and sometimes College Board will be tricky, and they may write it this way instead. Again, they still need infinity. They still need 0 for the index. Still need the n factorial. But instead of 4x to the n, sometimes what they like to do is just use x to the n. That way they can forego the parentheses. And then do 4 to the n, or even better yet, they'll do 2 to the 2n just to be clever. So again, these can be expressed in multiple different ways, just depending on how your answer key or whatever you happen to be looking at formats it. So that's the answer to number 3. That's your Maclaurin series. Again, it is centered around 0. Okay, on to example 4. Okay, same sort of thing. I'm going to use the Maclaurin series for 6 cosine of square root of x. And I realize that the cosine of x, I know. Here it is right here. Okay, again, we're going to piece this together slowly. We don't want the cosine of x, we want the cosine of radical x, which is no problem. We just simply turn all the x's into the square roots of x, like so. And of course, since they all have even powers, they're going to simplify real nicely. The square root of x squared is simply just x. This is x squared, x to the third. And finally, last but not least, this will end up being x to the n. So I'm going to neaten that up just a little bit. Okay, let's see if we can turn this into some sort of a summation. This part right here. But we already have the formula, so we'll just take that and we'll throw it inside a sigma. So let's see, we've got negative 1 to the n. We've got x to the n over 2n. That's factorialized. Again, we're going to put a sigma in front, going from 0 to infinity. The only thing is, we have not dealt with this 6 yet. Well, multiplying by 6 would just multiply each of the terms by 6. Rather than putting a 6 on the inside, however, I can just throw a 6 out front. It does the same job, and so this is going to be my formula for the Maclaurin series. And again, it is Maclaurin because you can see that it's just x minus 0, if you will, to the end. So it is centered at 0. So that's the answer to number 4. In my example number 5, we're going to have f of x is sine squared of x, and it says find a power series. This is using a known series, which is awesome. That means we don't have to generate it. Unfortunately, we can't just square a series easily. Sine squared of x would be sine of x times sine of x, and you can FOIL that out. The problem is sine of x goes on forever, and so, that would be kind of terrible to have to FOIL two things that are both infinite. So there has to be another way to do it, and there is. I go to the dark depths of the golden sheet, the bottom of the front side to the half angle formulas, and I pull out sine of x over 2. Hopefully you remember that from our golden sheet quizzes. That's going to equal plus or minus big square root 2 in the denominator of that root. And again, sine is minus, so it's going to be 1 minus. And these are always cosines up top. And it's cosine of x. This is always twice as big as the original angle. Okay, so we're going to take that. Speaking of twice as large, let's do this. I'm going to double both of the circles. So I'm going to make this a full-size x. All that's going to do over here on the right is keep the same formula, but it'll be 1 minus cos of 2x up top. And then I'm going to square both sides. So if you square this side on the left, it just becomes sine squared. If you square this, you don't need the square root anymore. In fact, you don't even need the plus minus. So it simply becomes 1 minus cos 2x over 2. So I'm going to make that substitution. And in fact, I'm going to go ahead and do it one better. I'm going to split these into 2 separate fractions, so that'll be 1/2 minus 1/2 cos 2x. I think that'll be easier to work with if I do it like that. Okay, now let's go ahead and see what that makes. Okay, I'm going to take this first 1/2 right here and just simply write it. So again, sine squared of x is what we're trying to find. 1/2 minus another 1/2, but this time we're going to figure out what the cosine of 2x is by using a known series. I know what the cosine of x is. The cosine just simply starts out with a 1, and then it's minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so forth. You get the minus, with the 6th power and so forth. And so forth and so on. Except we're not doing cosine of x, we're doing cosine of 2x. So I left the x out because I knew I'd be putting a 2x in its place. Okay, so we have this. Okay, now I can start bringing some terms down. We have 1/2. But immediately that's going to cancel with this minus 1/2, which is great news. Negative times negative will be plus. And that'll simply be 2x squared. But this time we're going to have a 2 on the bottom along with the 2 factorial that was there already. Okay, negative times positive is going to be a minus, and the signs will just alternate. They'll just alternate in a different way. And again, this 2 is on the denominator all the time, but then it's times 4 factorial. I'm going to do another term even though I didn't write it. We use the 6 factorial just so you can see the pattern one more time out. I guess technically this would be a minus here. And then the generic term is going to have the token 2. But this time, instead of 6, 8, 10 factorial, we have to make it generic, like I said. So we're going to use a parentheses. It's factorial, but 2, 4, 6, 8, 10, those are all multiples of 2. So we'll just use a 2n. And then the numerator, it's going to be an alternating component, so you're going to have a little negative 1 up there. It's going to be negative 1 to the n plus 1 power. And again, you can see that I want it to start with a certain sign and then alternate. I want it to alternate all the time. That's why it's not 2n plus 1. These are all 2x's up here, but they are going to the 2n. That keeps the odd powers out. Woo! All right. So basically, these first two cancel. The 1/2 and the negative 1/2 cancel. And everything else left over, I have to turn this into some sort of a sigma notation. I can use my generic part to do that. I'll just simply start at 1. I'll go to the infinity, and I'll write that. And that'll end up being my answer. And there you have it, the power series for number 5 for sine squared of x. Okay, a little different here. We want to find the first 5 non-zero terms of the Maclaurin series by multiplying or dividing the appropriate power series. So we have e to the x, and then we have arctan, or inverse tangent of x. Those are both memorized series. In fact, here they are. Now I'm going to go ahead and, since we're going to do a super mega foil, I'm going to clear out some serious space for this on a blank sheet of paper, and then I'll meet you there. So here we go. There, that looks better. One more thing just before I start doing all this foiling, I'm going to get rid of the factorials. I think that'll just make it a little bit easier for me to multiply. So 2, 3, 4, 5 factorial I'm going to replace with the regular numbers that I know. Now I'm ready to get after it. We'll go ahead and start the FOIL process with this x, and I'll send it back into the other parentheses, multiplying by all the terms. So we're going to have x plus x squared plus 1/2 x to the third plus 1/6 x to the fourth plus 1/24 x to the fifth plus, if I need it, 1/120 x to the sixth. I say if I need it because the direction said find the first 5 non-zero terms. I'm hoping that nothing cancels out. That way I won't even need the 6th power terms, but just in case I have them. All right, let's change colors, and this time we'll take the negative 1/3 x to the third, and we'll bring it through to all the other green ones, and we'll see what we have there. And that's going to end up making negative 1/3 x to the fourth, so I need to make sure to line that, I'm sorry, negative 1/3 x to the third. I have to start with a 1. So I will line that up with the other thirds, get all the like terms together. Minus 1/3 x to the fourth. Minus 1/6 x to the fifth. And I guess I could go 6ths as well. Oh man, I don't know if I want to do it though. Sure, why not? So it's going to be, let's see, minus 1/18 x to the 6th. I'm praying I don't need the 6th powers. Okay, then finally, let's go back to black. We'll take this 1/5 x to the 5th and multiply it by everything. So 1/5 x to the 5th times 1, of course, will be 1/5 x to the 5th. We'll line that up with the others. And you know what? At that point, I can stop. I don't have to go any farther because I can see that in the first 5 terms here, nothing's going to cancel out. So I can write the final answer. And here it is. I'll start with first power. I have x plus x squared. Let's see, 1/2 minus 1/3 is going to be 1/6 x cubed. So the cubes are done. 1/6 x to the fourth minus 1/3 x to the fourth. 1/6 minus 1/3 would be negative 1/6 x to the fourth. That's 4 terms. And finally, I have some x to the fifths. Oh boy. Let's see, we're going to have to make common denominators. 1/24th. Let's make the common denominators all 120. So 1/24th would be 5 over 120. Negative 1/6 would be negative 20 over 120. And then 1/5 would be 24 over 120. And that's going to add up to, let's see, what is that? 9 1/20ths, which is 3/40ths if I reduce that. And that is the answer. Okay, so that is e to the x arctan x, first 5 non-zero terms of the series. Whew.